Good morning. My presentation is mainly about an exploitation method that can be applied for use of the phrase Adobe Flash. My name is Guanxing Wen, and here's a brief introduction of myself. I'm a security researcher of Pangu, and previously, most of my time was focusing on Flash security, find its vulnerabilities, and keep track of the state of art of exploitation. And many of the bugs I report to Adobe are also made public through Internet Bug Bounty. I'm currently the top one contributor for this platform, and maybe forever, since HackerOne has stopped accepting new Flash vulnerabilities. In their opinion, they think Flash exploit no longer have the same impacts as when they start, so they will shifting the bounty resource to open source infrastructure. And the method we're going to talk about today is developed during the research of CV 2016-197, which is the use of the free discover and report to Adobe this May. So here's the agenda of my speech. I will start by introducing the basic ideas of how classical Flash exploit works and how recently mitigations prevent the classical trick. Next, I will show my method, which can bypass these mitigations, and then we'll build the exploit step by step with this method for CV 2016-197. At the end of the talk, I will also discuss how to exploit under 64-bit environment and how Windows 10 affects the exploitation. So for the past 3 years, maybe more, the classical Flash exploit is mainly about corrupt the length field of a vector object, no matter what type the bug is. So for example, heap overflow. And the exploit will start by spraying vectors and leak memory holes by freeing some of the vectors, so that when the vulnerable buffer is created, it will occupy one of the memory holes and corrupt the length field of the vector object by triggering the overflow. The vector with a very large length will be used to search the process memory for rope guards, shellcodes, and buffers, all kinds of structures you might need for exploit to work. And then finally, the rope chain will be triggered by a fake word function table. And when it comes to use of the free, the process is very similar. With the proper heap memory layout, the vulnerable object following one of the memory holes will be released because of use of the free and then occupied with controlled vector data. And after that, when a member function or member property of this downlink pointer is invoked, a fully controllable memory write will corrupt one of the length field of the vector object. And when we find that corrupted vector, everything else goes like that of heap overflow. Since the length field is located at the beginning part of the vector buffer, it is very convenient to be corrupted with virus of Flash, even browser vulnerabilities. So this technique has been very popular for the past years, mainly because Adobe only fixes the vulnerability itself instead of mitigate the exploitation method. So finally, last December, the popularity of hacking team's Flash exploit played a major role for Adobe's final decision. So working with Google Project Zero, Adobe adds mitigations to vector, and after the mitigation, the length field is moved to the metadata part of the vector object, only left with the verification field in the same position. Since the length field and the verification field are now in different memory block, corrupt them at the same time is not practical. Besides the vector mitigation, Adobe also adds verification fields to byte array, which is another very popular array-like structure that is widely used in exploit. Well, the length field and the verification fields are now still staying in the same memory block, although very rare. Powerful zero-day exploit, including those used by Pontoon, were able to read the verification field first and then calculate the security value by XOR the length field and the verification fields, and then corrupt them with the new value at the same time. But this behavior highly depends on the quality of the vulnerability. To read and then corrupt almost means the bug itself is capable of read and write any piece of the memory, let's say a type confusion. So even without corruption of the byte array, the vulnerability itself can finish the exploitation. And to crop byte array just make the exploit code simpler to write. And besides the length verification, isolated heap is also introduced into Adobe Flash. Right now, there are many heap partitions inside Flash. Well, this technique is first explained in Google Project Zero's blog. And basically, the data and the object are now separated into different memory blocks. So even if there's a use of the free, we cannot control its memory with vector or byte array anymore. Yet it is still possible to control the freed object with other class objects in the same heap partition. And that is something we're going to use later for our exploit to work. So in summary, the mitigations had disarmed the classical and popular Flash exploit method. Before the mitigation, there may be 2 or 3 Flash exploits in the wild for months, but after the mitigation, there may be just 1 or 2 Flash exploits in the wild for half a year. So the mitigation itself is very useful and powerful. And today we mainly focus on use of the free. Let's see how to bring this type of bug back to life. So what is really necessary for use of the free bug to work? In my opinion, I think a read primitive helps a lot. And that is the past year's Flash exploit all shares. So right now, only with the read primitive can you find rope guards and buffers to store the shellcode and wrappers to set executability of the shellcode. As we're talking about use of the free, we're able to fake the virtual function table by just memory occupation. So a write primitive is not a necessity. Currently, exploit can read primitive by tempering the length field of a vector object, byte array, and other structures that works like array. Well, our approach is to temper the start address of the array-like structure. Also, byte array and vector are not only candidates. There are other array-like structures inside Adobe Flash. And for proof of concept, I will start with the simplest array-like structure, the string object. So if a class holds a string inside, a structure will be something like this. There will be a virtual function table, a reference count, other fields, at least contain a buffer and length dedicated to a string. But the string here I'm talking about is not an ActionScript string. So if it is really an ActionScript string, it will be just a reference pointer here instead of a buffer and length. But some class, they choose to store the string inside with no further operations. So they will use a self-defined light-weighted structure inside of the heavy-weighted ActionScript string. So somehow, with the help of use of the free, we're able to release the class memory and then control this memory by occupation, where the start address of the string object can be any desired value. Right now, we're able to access the target memory through the string object. And after dealing with the target memory, let's assume we can release this class memory again. And in the real-world case, I will show you how this step can be done, but currently, let's just assume the step can finish itself. So when the class memory is released again, we can occupy it with another bunch of data, where the start address can be another value. And with such release and occupation over and over, the string object becomes a read primitive. And that is the main idea of our exploitation method. Since there were many cycles of release and occupation, the method is named as use of the free. But this is maybe too ideal the situation. So let's come back to the beginning of the use of the free. When the vulnerable object is released, its structure may not contain a string inside. So we should occupy its class memory with other classes, our selected classes, which holds a string inside. And after because of isolated heap, this two-class memory should also stay in the same heap partition and in the same size. So after occupation, when we invoke the virtual function of the downlink pointer, it is now the virtual function with the same offset, but in the selected class memory being indexed. The key point is that such type confusion status wasn't expected by any of the functions. So this unexpected behavior may help us release the class memory. And then we are in the read primitive situations that we have discussed before. So here are the basic steps turning a use of the free into a read primitive. But these are all abstract concepts. So let's go through a real-world case to see how this actually works. CV 2016-197 is a use of the free I discovered in PSDK class. PSDK belongs to media core package. I discovered this package, I think this package is first introduced into Flash version 19. And I discovered this package by decompiling the player global file and cross-comparing it with its old version. There were many classes under this package, but all of these classes are undocumented. There is only some related information can be found from another Adobe products called Primetime Player SDK. This SDK is mainly used to develop TV-based cross-platform application. And for the PC environment, the SDK is a bunch of ActionScript files. So my best guess is that the package I found is a native implementation of this SDK inside Flash Player to accelerate the running speed. Apparently, when the first time this package is introduced into Flash, it haven't been thoroughly tested. I found many memory corruptions last August, and after reporting them to Adobe, they choose to remove the entire package from its next version. So for that moment, I just think maybe the whole package shouldn't be exposed to the developer. But after half a year, the whole package is back into Flash version 21. So the truth behind is fix all of these memory corruptions takes time. So Adobe used half a year to fix all of these bugs and reintroduce them into Flash version 21. And the use of the free we're talking about here is discovered right after PSDK and the media core package is back. Here's the code snippet to triggering the use of the free. The only way to get an instance of PSDK is through its statical member property called little capital PSDK. So apparently, the class memory is constructed and initialized by ActionScript virtual machine, the AVM itself. So naturally, the class memory should also be destructed and cleaned by AVM automatically. But the weird part is that this class also contains a method called release, which can be invoked directly from the ActionScript level to explicitly release the class memory of PSDK. Well, this is rarely the case for ActionScript objects. Normally, out-of-Flash objects are completely managed by MMGC, the garbage collector. So the only way to actually release the class memory is you just don't use them. So the reference count of this class will be 0. And MMGC will scan all the objects and find the proper moment to actually release the class memory. But as this class is undocumented, so we don't know if this release is necessary or not. But at least the reference count wasn't cleaned after release. So the atom reference pointer is still pointing to the class memory after release. And when we invoke the virtual function with this pointer, there goes the old textbook use of the free. So the root cause of this vulnerability is very easy to understand. Let's go build the exploit. PSDK takes 32 bytes. There are 2 virtual function tables at the beginning of this class memory. All the member functions that can be invoked from the ActionScript level are indexed in the first virtual function table. And the destructor is indexed in the second one. But the destructor can only be invoked by MMGC. Other fields of this class are irrelevant to our exploit, so I will skip a thorough demonstration. So after PSDK is released, we should occupy its class memory with another class, as we discussed before. So I manually checked all the classes under media core package. I think they are most likely the best candidates. Classes under the same package are very likely to implement in a similar way, especially for their heap partition. So finally, after several checks, I picked track. It contains 2 string fields. And after memory alignment, track is in the same size of PSDK. So meaning that when PSDK is released, newly constructed track will then occupy its memory. And right now, when we invoke the virtual function of PSDK, let's say the create dispatcher located at 14 hex offset, it is now the virtual function of track being indexed. And this type confusion function call treats the second double word of current class memory to be a reference count, decrement it, and release current memory if the reference count is 0. So this type confusion call is very like a destructor. And the second double word of current class memory is happen to be the length field of the first string object inside track. So simply initialize track with a single character string can we control this field to be 1, and after decrementation, the memory of track will be released. And right now, we have a downlink pointer in type of track that is created by us. But we still need to find a way to occupy the memory of track to control its content and release the class memory again. And there I will introduce you set byte array, which is a very handy function that almost born to finish the task that we have left. It can occupy the memory of track and then release it at the same time. So set byte array simply duplicate the input byte array inside metadata. And metadata also belongs to media core package. So it is sharing the same heap partition with track and PSDK. Set byte array will allocate a temporary space to pre-processing the input byte array. If the encoding and the length is okay, then set byte array will allocate another memory to save the content of this byte array and save the pointer inside metadata. Since this temporary space is first allocated, if the input byte array is 32 bytes long, the same size of PSDK, the temporary space is what occupies the memory of PSDK. So we can just use a 32 bytes long byte array and evoke set byte arrays. The memory of track will be controlled. And the best part of this is when at the end of the set byte array, this temporary space will be released explicitly. So meaning that the memory of track fitting with controlled content is still being freed, waiting for next occupation. Recall from the last part, when PSDK is released, track takes its position, and type confusion function call release track memory again. And for the read primitive part, each time we want to read access the target memory, we just use set byte array with a 32 bytes long byte array, which is 16 offset to be the target address. This 16 offset is happen to be the second string field inside track. So after set byte array, when we invoke track.longRange, which is the second string field, we can access the target memory. Right now, I just set the string length to be 4. There is no need to be a large number, 8, 1,000, as the returning of the string object contains an encoding problem. So if there's some special character in the string memory, in the target memory, the returning of the string will be broken. And in that case, we still need to read the target memory character after character. So I just set the length to be 4. So in most cases, the returning value will be 4 bytes long. It can easily convert it to be int value, very convenient to deal with other part of your exploit. So right now, we have the ability to read any part of the memory. I think everything else can only limited by imagination. There will be many options. Let's say we can read a stable location spread with vector object. A vector object is filled with current class pointer, this. And although vector cannot be used to be cropped, it is still a very feasible way for heap spree. So when we read a stable location, we know that this pointer is located right after the metadata of vector object. And with this pointer, we can easily find all the self-defined variables inside our class. Let's say we can find the byte array, the string, the track, vector, and they're all started with 54 hex offset. As we know, with simple reverse engineering, you can know the structure of these classes. So you can find a buffer inside to store shellcode, rope chain, fake virtual function table. And this trick is firstly used by hacking teams' Flash exploit. It is very efficient. There is no need for brute force searching of your self-defined variables. And after that, we can use one of the virtual function table of this class to find a module base of Flash and start to search the rope gauges for exploit. And after every buffer is filled, linked, setBat array is invoked one more time to crop the second virtual function table of PSDK. The reason we choose the second virtual function table instead of the first one is that, as you can remember, it is the temporary space that occupies and controls the memory of PSDK. And the release of this temporary space has one minor side effect. It modifies the first byte of current class memory, meaning that we cannot fully control the first virtual function table. So we choose the second one. We can crop the second virtual function table pointing to our rope chain. The second virtual function table belongs to the destructor of PSDK. So after every exploit code that we have written in the Flash file is executed, MMGC will kick in and try to release other class memory. And that is the moment our rope chain is being executed. The rope chain simply point EX to a controllable memory and invoke a wrapper inside Flash. So this wrapper is very convenient. You just invoke point EX to a controllable memory, make sure EX -8 and EX -4 pointing to the start address and the length of the shellcode, and then wrapper will invoke virtual protect inside to set the executed bit of the shellcode and then jump over. This wrapper code is firstly used by CVE 2014-0515. The searching pattern for this wrapper hasn't changed ever since until Flash version 22. The reason for this changing is a new mitigation called memory protector is introduced into Flash version 22. But as this new mitigation doesn't affect our exploitation or the vulnerabilities, so I have skipped its demonstration at the mitigation part. But I will mention this mitigation later in the conclusion. So after invoke the wrapper, and then we'll jump over to the shellcode. As a demo, the code is running under 7. The read primitive part will be a little time consuming, as you can see there are 6 or 7 lines for the exploit to work, for the read primitive to work. This is highly weighted compared to the traditionally vector plus index number. So currently, what we have discussed is under 32-bit environment. What about 64-bit environment? First thing, the pointer is changing from 4 bytes long to 8 bytes long. And many classes are in different size. As a result, PSDK and track, these two classes are now in different size, so they cannot occupy each other. We should find another class to occupy the memory of PSDK, and that is media resource. Media resources and also under media core package. So it is sharing the same heap partition. And it contains string inside. So after PSDK is released, media resource will then occupy its memory. And this time, the type confusion function call will treat the F0 hex offset to be a reference count, decremented release current memory if the reference count is 0. So this is very similar with 32-bit. But except this time, we cannot control the F0 hex offset memory with media resource itself, because F0 is a very large number, and this memory is out of bound of media resource. Media resource is only 40 or 50 bytes long. So we should occupy and control this part of memory before PSDK is released. There are 2 reasons why we can invoke setBat array one time to control this part of memory. The first reason is that PSDK and track and media resource, all these classes we have discussed under media core package, they're using a different heap partition compared to traditional Flash objects. Traditionally, all the flash objects are completely managed by MMGC, where virtual alloc on self-defined flash heap. But for these classes we have discussed, they're managed by malloc and free directly on the default heap or the CRT heap. So that means the memory of PSDK and these classes are very pure. There won't be any interference of the memory of the PSDK into our set byte array. So when set byte array is invoked, it is the first time the memory after PSDK is allocated. So that is the reason we can control that part of memory. And the second reason is PSDK take 40 or 50 bytes, and there are 2 memory blocks inside byte array, as you can remember. So these 3 memory blocks added together help us control the memory of F0 hex offset. Then we can set that value to be 1. And this time the type of confusion call can works correctly and release the memory of media resource. So again, we are in the read primitive situation. But this time we cannot just read a stable location sprayed with vector object anymore. Since traditional flash objects under 64-bit environment are high 32-bit randomized, so even we have sprayed terabytes of memory, we cannot control a stable location with our controlled data. Luckily, I find that spraying malloc flash objects doesn't derive the high entropy under Windows 7. So I just choose another class under media core package. It is add asset. As you know, it is malloc. So add asset works like an array. The class inside will duplicate themselves and spraying the memory when we invoke the constructor. All the class memory will be, their high 32-bit will remain 0. So we can start to brute force searching this sprayed memory. And one of the class being sprayed is media resource. As you can remember, it contains a string inside. Also, there is an int value. So this int value can be used as a flag. When we find that flag during the brute force searching, we know that media resource is here and metadata is adjacent. Metadata can be used as a replacement of vector and byte array. It contains a buffer inside, just like vector or byte array. And this buffer can be easily found where fixed offset. Only to notice that the offset for the second step is calculated via hash function. The hash value is only 0 to 7, and the input value is the key names, that is the first parameter of set byte array. There is very likely a hash collision, but we don't want any hash collisions. Or otherwise, there will be a list structure inside metadata, and finding the buffer inside will be very much difficult. So we just choose different names and make sure their hash value is different, as we don't need so many buffers. So after all of this has done, we can find all the buffers, and these buffers can be filled and linked just like 32-bit, and the fake virtual function type of trick works just like before. So currently, all of this has been discussed under Windows 7. What about Windows 10? First, I didn't intend to build a fully workable exploit under Windows 10. As for Windows 7, there are many new things, new mitigations, new heap spraying method, and new heap partition. Also, there are a lot of reverse engineering of all the classes under media core. So I don't want to do all of this under Windows 10 again. I just need to take a quick peek to see what's the difference for Windows 10. First, PSDK is still malloc on the low fragment heap, the LFH. This is absolutely the same with Windows 7. But LFH itself is changing from Windows 7 to Windows 10. There is a heap randomization added into Windows 10. So for Windows 7, when the memory of PSDK is released, it comes down to the end of the free list. And when next allocation is coming, the last memory block being freed will be the next one being allocated. So it is very predictable. We know that the memory of PSDK will be occupied with just one occupation. with just one allocation. But for Windows 10, there's a bitmap controlling the low fragment heap allocation. But we can still use the free list model to explain what happened. So when the memory of PSDK is released, it comes down to the free list. Let's say there is 16 blocks in this free list. And when next allocation is coming, LFH will randomly choose one of those 16 blocks to be the next one being allocated, meaning that we don't know if the memory of PSDK is occupied or not with just one allocation. So a direct idea to bypass this is multiple occupation. As you have said, there are 16 blocks, so why not we just use 16 allocations, make sure the PSDK memory is occupied. But this is only partially correct. As you can see, for the first 15 allocation, everything goes normal. But for the 16th allocation, LFH won't use the last memory block inside this free list. It will allocate a new free list and choose one of those memory blocks to be the next one being allocated, just to enlarge the randomization. But this randomization is still limited. After 2 or 3 cycles of free list allocation, LFH will finally realize that, well, I still have a memory block inside the first free list, and why not using it? It's a waste. So that is the moment LFH will allocate the last memory block inside the first free list, and that is the moment we know the memory of PSDK is occupied. All of these demonstrations is based on black box heap experiments, but I have discussed with other people who have done fully reverse engineering of NTDEL to see how LFH works, and all of these demonstrations has been confirmed. So meaning that after PSDK is released, we can construct track hundreds of times, and this will make sure the memory of PSDK is occupied. And this time, the type confusion function call actually makes things easier for us. We don't need to control any part of the memory. Just pass the parameter to be 1, and then the memory of track will be released. And then we're in the read primitive situation. But this time, still for the situation, we need multiple occupation, meaning that for each cycle, we need to use multiple set byte array to control the content of track. But I didn't go any step further. So although Windows 10 brings us a tough environment, use after free may still find its way for a read primitive. So for the conclusion part, first about the fix. After reporting this issue to Adobe, their fix is manually remove the reference pointer from the ActionScript level, which is used to invoke release. And when I said manually, meaning that this fix can be bypassed. So there goes another vulnerability, CV 2016-4048. And I bypassed this first fix by declaring 2 references pointing to PSDK, and invoke release with one of them, but triggering the use of the free with another. And to exploit the second vulnerability, I find that there's only one line change necessary for the exploit to work, only the triggering part. But when I try to exploit the second bug, it is now Flash version 22. As I have told you before, it was a memory protector. A new mitigation is added into Adobe Flash. Memory protector is used to delay the free of objects. Mitigation mainly used for use of the free, and maybe something learned from Microsoft IE. But this mitigation doesn't affect our exploitation or the vulnerability, even if we're talking about use of the free. The reason for that is memory protector maybe only focusing on objects that are managed by MMDC, not our malloc and the free managed objects. Or maybe this memory protector only focusing on stack pointers, but our pointer is saved in the heap inside PSDK. But I haven't given it a thorough analysis, as it doesn't affect my exploitation. So for the second fix, Adobe chose again to remove this function from ActionScript level. So if they really don't need this function, why should they introduce it at first place? So maybe this is just another temporary fix, just as before. I've met such temporary fix many times before. So once I have a heap overflow, and after a patch, the heap overflow is gone. And the reason for that is the heap memory is doubled. So my heap overflow cannot overflow that much of memory, and that is the reason it's gone. But after several versions of Adobe Flash, the bug is back. So I check the code again, I see the calculation of the heap memory is rolling back. So the truth is, the first fix is temporary fix for some other people's heap overflow. But after several versions, after Adobe figure out how to calculate the right size of the heap, they're rolling back to the old calculation. But that doesn't fix my heap overflow, so it is back. So if this fix is actually a temporary fix, after several versions of Flash, maybe it will come back. If still they use manually remove of this pointer, there may be still a bypass. So for the use of the free, I think it's a relatively common way to exploit the use of the freeze in Adobe Flash. Although the first part that use a type confusion function call to release the class memory seems a little complicated, but I have accomplished this under 3 versions of Adobe Flash, the 32-bit and 64-bit and Windows 7 and the 32-bit and Windows 10. So I think it is still practical, only you need a lot of reverse engineering. And currently we're dealing with a string object and thus gave us a read primitive. And in the future, if we can find some other array-like structure to crop with, maybe we can get a write primitive. And that will be much helpful for the exploit to work and the Windows 10. And the problem for the string object is when you try to read the target memory, everything goes well. But when you try to write the target memory, it will allocate a new buffer to save what you're going to write and then save the pointer inside. So we cannot just write any target memory, but if you can find another array-like structure which use the target address to be the one written in, that is, we can find a write primitive. And the idea behind the use of the free, I think, is more common, as I have seen such release and occupation and type confusion things in an iOS kernel exploit. So I think this method, the idea behind this method, can be implemented in other platforms and softwares. So that is all for my presentation. Thank you very much.